Good morning and thank you for the assistance. Now I will present the results obtained during the development of the work entitled Analysis of Glide-Symmetric FSS Structures from a Circuit Model Standpoint. This work has been done in collaboration with the University of Granada, the Polytechnic University of Madrid, and the University of Seville in Spain. This presentation is organized according to the following topics. We will start by introducing the motivation of this work. Then, we will present the derivation of the circuit approach for the analysis of glide-symmetric stack FSS. Finally, we will present some numerical examples related to stacks of two-dimensional aperture arrays and the study of the dispersion properties, dispersion diagram, and block impedance of infinite periodic structures, namely three-dimensional periodic FSS. Let's start by recalling what a frequency-selective surface is. A frequency-selective surface of FSS is any artificial structure that controls the scattering properties of incident electromagnetic waves. For that reason, they have widely used for the design of polarizers, filters, absorbers, and a wide variety of microwave and photonic devices. Among of the possible configurations, periodic arrangements of apertures and patches are of particular interest due to their simplicity. However, traditional configurations use a single layer embedded in a dielectric media. Nonetheless, it is well known that by stacking several layers and breaking the alignment between these consecutive and adjacent layers, this is known to bring multiple benefits to the structure, such as increased bandwidth or the appearance of new transmission peaks. In any periodic configuration, the scattering parameters can be derived from a general waveguide problem, which is a combination of electric, magnetic, and periodic boundary conditions. This means that our frequency-selective surface can be simply analyzed by simply considering the unit cell of these generalized waveguide problems, and this means that this unit cell and the whole FSS admits to be represented in terms of canonical circuits. These are the electric and magnetic fields that we are considering in our approach. They are represented as an infinite sum of floquet harmonics, and we should state that the fundamental harmonic is clear outside the sum and carries the information about the reflected amplitude. This is the coefficient R. By simply projecting the electric and magnetic fields on a single basis function, which is of our choice, we will eventually arrive to the following expression of the reflection coefficient R, which is mainly dominated by three terms. The first term is related to the input media, which is represented with a transmission line. The second term is represents the output media, which can be also represented with a transmission line, and the middle term is the equivalent admittance that represents the discontinuity plane in the structure. This will be the simplified version of the circuit, but we are especially interested in obtaining an expanded version of the circuit. This will be of interest in order to construct the equivalent circuit for stacked configurations. By simply expanding the equivalent admittance, we will arrive to the following equivalent circuit. This is the equivalent circuit of a single layer, and the expanded version of this layer will help us to form the equivalent circuit of a two-layer stack. This can be simply done by joining the two equivalent circuits of two different single layers, as represented in this animation. This will be the expanded version of the equivalent circuit. However, for the sake of simplicity, we are interested in obtaining the simplified version of the circuit, similarly to the previous single layer case. In this case, in order to simplify the circuit, we can divide the whole circuit into three different regions, which represent the internal, or what we call the internal and external regions. In this case, we can take advantage of the parallel connections related to the aperture problem, and we can simply join together and group together by simply summing the different individual blocks, admittance blocks that you can see in this figure. We can do the same for the external regions, the input and output external regions, and at the end, we will arrive to the following simplified circuit for a two-layer FSS, which is represented by two external admittances and one internal admittance block. This procedure can be extended for a general n-layer case, and we will eventually arrive to the following circuit, which is represented by n-1 internal admittance blocks and by two external admittances. Before continuing and showing some numerical examples, first of all, we should state that the proposed formulation is an analysis method, not a synthesis method. In the formulation, we are assuming that the tangential fields are expressed with frequency-independent aperture profiles. This means that our circuit is valid up to the second excitable resonance of the considered aperture. Furthermore, we are considering that the aperture fields are estimated independently, without coupling between layers. As we will see, this leads to a very good results. However, the key formulation of the circuit is that linear transformation between consecutive layers can be dealt from a purely analytical perspective. This would be the case of displaced or misaligned layers, which for a particular case leads to the glide-symmetric version of a stacked structure. This would be the case of rotating adjacent layers, which is of interest for studying twist symmetric structures, another kind of higher symmetric configuration. Also different layers or different apertures that form the different layers can be scaled among each other. The first numerical example we are considering is a stacked FSS formed by a pair of closely spaced perforated layers, arranged in a glide-symmetric configuration. As it can be appreciated in the slide, there is a very good agreement between our circuit approach and the commercial software CST, even for such a reduced spacing between layers as λ/50, which is represented in the rightmost image of the slide. Therefore, it is demonstrated that the approximation of considering isolated aperture profiles works reasonably well, even in such an extreme benchmark scenario. Then we present the analysis of a 10-layer stack formed by annular apertures, as it can be appreciated in the figure. We will compare a mirror symmetric version and a glide symmetric version of the same structure. As it can be appreciated, for the mirror symmetric case, there is a very good agreement between our circuit approach and the reference results in the following citation, the following reference, sorry. This would be the glide-symmetric version of the same structure. In the glide-symmetric version of this structure, even layers, that is layers number 2, 4, 6, 8, and 10, they are off-shifted half a period compared to the odd layers. These are the results comparing our circuit approach and CST, and there is a very good agreement between both results for such a complex spectrum as this one. Finally, we will consider the analysis of infinite periodic stacks along the longitudinal direction. This is what we call three-dimensional stacks. The dispersion diagram of these structures can be computed from the ABCD parameters of a single unit cell. This will eventually lead, in our case, to this expression, to the expression that you can see in this slide, which essentially represents the dispersion relation of this structure, the mirror symmetric configuration. Now we can also see the dispersion diagram in both phase and attenuation constants, and we have also compare our circuit approach with CST. As it can be appreciated, there is a very good agreement. We should note that the different Floquet modes that are actually excited in the structure, they are represented in the circuit with different basis functions. These basis functions are associated to the colors, to different colors that you can see in the electric field profile of the annular aperture. This would be the case of the blue curve, the red curve, the green curve, and so on. Furthermore, we should state that our circuit approach is also able to extract the attenuation constant of the structure. And this is a very valuable feature since most of our commercial eigenmode solvers cannot compute the attenuation constant of periodic structures. This would be the Glide-Symmetric version of the same three-dimensional stack, where the even layers are off-shifted half a period in both x and y directions, and by applying a similar procedure, we will eventually arrive to this dispersion relation. We have also compared the phase constant results with CST, with commercial software CST, and there is a very, very good agreement between both results. We have also plotted the attenuation constant of the structure, in this case for the first mode, which is related to the blue curve in the figure. The present formulation is also able to compute the block impedance of a three-dimensional periodic structure. In this case, we have computed the block impedance of the first three propagated modes for the mirror and glide-symmetric configurations. It can be appreciated that the real part of the block impedance of the first propagated mode, which is the blue curve, is near the value of the free space impedance, that is 377 ohms. This means that a good matching, a good transmission is expected for this mode. However, the second and third modes, which are represented with red and green curves, they have a very low value of the block impedance. So these modes are mainly reflected and hardly transmitted in the FSS. Finally, it is observed that the ripple in the passband is higher for the glide-symmetric configuration. This can be explained by comparing the value of the block impedance in both glide-symmetric and mirror-symmetric configurations. Note that the block impedance of the mirror case in the blue curve is nearer the value of the free space impedance, so its ripple is lower. Now we will summarize the main conclusions extracted from the work. We have seen that non-aligned layers, non-aligned stacked structures, in this case, we particularize to glide-symmetric configurations, that they can bring multiple benefits compared to single-layer structures, such as the appearance of new transmission peaks or an increased frequency bandwidth. For the analysis of this kind of glide-symmetric configurations, we have presented an efficient and rigorous circuit approach based on a Floquet modal expansions. We have seen that it is quite useful for the design of wideband polarization rotators, absorber, matching layers, and other microwave devices. We have validated numerically these results by analyzing different stacked structures with canonical apertures, in this case with rectangular and annular apertures, and we have also plotted the dispersion properties of longitudinally, that is three-dimensional periodic configurations. So thank you for your attention.